Hello, welcome to a video on the motion of charged particles in magnetic fields. The image here is of an electron beam within a cathode ray, and the electron beam is being deflected by a magnet. So if a particle has charge or if there is a current running through a magnetic field, it will be deflected as a result of force. Cathode ray tubes were used in the early TVs, not so much anymore because I think they're pretty sizable and they wouldn't fit in the back of our massive flat screens now, but back in the day they were the go-to. So magnets, magnetic materials and current-carrying conductors all experience a force in magnetic fields. A magnetic force on a moving charged particle depends on both the magnitude and the direction of the velocity of the moving charge. The direction of the force on a current-carrying conductor or an individual charged particle moving at any angle of theta to a uniform magnetic field depends on the direction of the magnetic field and the direction of the charge movement. In Stage 2 physics, you'll need to be able to determine the direction of one of the forces, magnetic field or charge movement given the direction of the other two. So there's three different directions that correspond to three different things. You'll be given two, you'll have to determine what the direction of the other thing is, and we'll have a rule or a technique for doing that. You also need to be able to solve problems involving the use of these rules. So this one for the force on the magnetic force on a current carrying conductor, and this rule here for the magnetic force on a moving charged particle. So charged particles, current carrying conductors and magnetic materials all experience a magnetic force when they're moving in a magnetic field. We'll look at charged particles first. So for charged particles, the magnetic force is equal to the charge, which is Q, so that's in coulombs, times by the velocity, which is in meters per second, and that's the velocity of the charge, multiplied by the magnetic field strength, which is in Tesla, and then by the sine of the angle, which is measured in degrees, and that's of the charged particle's velocity to the direction of the magnetic field, so the angle between those. In order to determine the direction of the magnetic force, we use the right hand palm rule. So for determining the direction of a magnetic field around a wire, we use the right hand rule. This one's slightly different. It's called the right hand palm rule, and this is for determining the direction of a magnetic force. So to use this, your right thumb points in the direction of the positive particle's velocity, or if we're using current, then it will point in the direction of the conventional current. Your fingers point in the direction of the magnetic field, and then your open palm will push in the direction of the magnetic force. So you'll be given any two of these three things, and you'll have to work out the leftover unknown. If you've got a negative charge, you do the same, but you reverse the direction of the magnetic force. So just say we had an electron moving with a velocity. You point your thumb in that direction, your fingers in the direction of the magnetic field, but rather than the force acting in the direction that your palm is facing, the force will be acting in the direction that the back of your hand is facing. So remember, for negative particles such as electrons, there's just that slight adjustment, and remember to use your right hand when you're doing this, otherwise you'll have it back to front. So as an example, we've got a proton with a charge of plus 1.6 by 10 to the negative 19 coulombs, and it's got a velocity of 10 meters per second to the right. It enters perpendicularly to an upwards magnetic field with a strength of 4.0 by 10 to the negative 5 teslas, we have to find what the magnetic force exerted on the particle by the field is. So to work this out, we use our rule, which is magnetic force is equal to the charge multiplied by the velocity of the particle multiplied by the magnetic field strength and then by the sine of the angle. This is entering perpendicularly, so we know that the angle is going to be 90 degrees. From here we can just sub in our value, so Q is going to be 1.6 by 10 to the negative 19. Velocity is going to be 10 meters per second to the right. We'll take right as positive, direction, positive. And the field strength is 4.0 by 10 to the negative 5 teslas. So our magnetic field strength will end up being 6.4 by 10 to the negative 23 newtons. Now, if we want to work out the direction of the force, we know that it's moving to the right, so we'll point our thumb in the direction of the right, and we know that the magnetic field is upwards. So we'll point our fingers upwards, I guess towards the top of the page or to the top of the slide. So if you've done that, your palm will be facing, I guess, out of the screen or like out of the paper. So the magnetic force is acting out of the paper or out of the page. That's the direction that the force is acting in on that proton, so the proton will be pushed in that direction by the magnetic field. So I've got a similar example. It's just an electron with a charge of negative 1.6 by 10 to the 19 coulombs. The velocity is the same and it's also to the right. It's entering perpendicularly to the same upwards magnetic field with a strength of 4.0 by 10 to the negative 5 Tesla. What is the magnetic force exerted on the particle by the field? So exactly the same. Magnetic force is equal to charge multiplied by velocity times by the magnetic field strength and then sine of the angle. Just realised I forgot to do sine up here. Sine of 90 is 1, so that's just all multiplied by 1. So again, this will be 1.6 by 10 to the negative 19. I'm going to leave out the negative, and then I'm just going to remember that it's an electron we're talking about, so I'll need to make that adjustment with the right-hand palm rule. 10 meters per second is the velocity, and then the magnetic field strength is 4.0 by 10 to the negative 5 teslas, and this is all by sine 90, which of course is 1. So we've got 6.4 by 10 to the negative 23 newtons acting on this electron. Now if I do my right hand palm rule, my thumb is pointing to the right because that's the direction of the velocity. My fingers are pointing up because as into the top of the page or the top of the slide, because that's the direction of the magnetic field. And because this is an electron, rather than using the direction that my palm is facing, I'll be using the direction that the back of my hand is facing. So it'll be the force acting on the electron will be 6.4 by 10 to the negative 23 newtons into the page. So you'll also need to be able to solve problems for current carrying conductors, so the force acting on these current carrying conductors, and the rule that you use is this one here. It looks similar to the rule for charges, there's just some slight variation. So current, which is I, is measured in amperes, And then L, which is length, and that's the length of the current carrying conductor being acted on in the field. This is measured in meters. B is the mag field strength, and this is measured in Teslas. And then theta is the angle between B and the length of the wire, length of the current carrying conductor. This is measured in degrees. So as an example, a 1 meter wire carries 100 amps of current at an angle of 30 degrees to a magnetic field which has a strength of 5.0 by 10 to the negative 5 teslas. What is the magnetic force exerted on the conductor? So for this, our magnetic force is going to be equal to the rule current multiplied by the length of wire multiplied by the magnetic field multiplied by the sine of the angle of the current carrying conductor to the magnetic field. That's the rule that we're using. Our current is going to be equal to 100 amps. Our length is going to be equal to 1 meter. Our magnetic field strength is 5.0 by 10 to the negative 5 teslas, and our angle is 30 degrees. So you sub all of this in, 100, and then 1 meter for the length, and then 5.0 by 10 to the negative 5 teslas, and then sine of 30. Pop all of this into your calculator and you'll end up with 2.5 by 10 to the negative 3 newtons. So that's the magnitude of the magnetic force exerted on this conductor. We don't have any information about the direction of the magnetic field or the direction of the current, other than that it's at 30 degrees to the magnetic field, but we're not sure what orientation that is to begin with. So we'll just have to, we can only work out the magnitude in this situation. So 2.5 by 10 to the negative 3 newtons is the magnetic force exerted on this conductor.